Tonight, we're going to confront one of the most profound and unsettling questions in all of science. Are we alone in the universe? Almost certainly not. The numbers make it nearly impossible for Earth to be the only planet harboring life. But here's the twist that changes everything. Even if the universe is teeming with intelligent civilizations, even if there are millions of advanced societies out there right now, building cities and sending signals and wondering if anyone else exists, we may never meet a single one of them. Not because they don't exist, not because we're not looking hard enough, but because the universe itself, through the fundamental laws of physics and the tyranny of distance and time, makes contact between civilizations almost impossibly difficult. By the end of tonight, you're going to understand exactly why the cosmos is structured in a way that keeps intelligent life isolated, scattered across incomprehensible distances, separated by barriers that no amount of technology can fully overcome. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The question of whether we're alone has haunted humanity for as long as we've been capable of asking it. Ancient civilizations looked up at the stars and saw gods, spirits, other worlds. The Greek philosopher Epicurus, writing in the 3rd century BCE, argued that infinite space must contain infinite worlds. If atoms can combine to form Earth and life here, why not elsewhere? Giordano Bruno, in the 16th century, proposed that stars were distant suns with their own planets, possibly inhabited. His ideas were radical for the time, but they persisted. By the 20th century, science fiction had fully embraced the concept of alien civilizations. Stories of Martians and moon dwellers and galactic empires filled popular imagination. We assumed that if life existed elsewhere, we'd eventually meet them, trade with them, perhaps even fight them. But as our understanding of the universe deepened, something strange became apparent. The more we learned about the cosmos, the more we realized how extraordinarily difficult it would be for two civilizations to ever make contact. Not difficult in the sense of challenging, but achievable. Difficult in the sense of bordering on impossible. Let's start with the most basic barrier, distance. The universe is big. That's not a metaphor or an exaggeration. It's an understatement. When we say the universe is big, we're talking about distances so vast that human brains simply cannot process them intuitively. You can write down the numbers, you can calculate with them, you can use them in equations, but truly grasping what those numbers mean is beyond our cognitive ability. We evolved to understand distances we could walk in a day, maybe a week. A few dozen miles felt like a long journey to our ancestors. 100 miles was an expedition. 1,000 miles was an unimaginable voyage across the known world. But even 1,000 miles is nothing compared to the distances between stars. Now, we're talking about distances measured in light years. A light year is how far light travels in 1 year. Light moves at about 186,000 miles per second. In 1 second, light can circle Earth more than 7 times. In 1 year, light travels about 5.879 trillion miles. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. That means it's roughly 25 trillion miles from Earth. If you could somehow travel at 1 million miles per hour, which is far faster than any spacecraft we've ever built, it would still take you over 2,800 years to reach Proxima Centauri. That's longer than all of recorded Western civilization. When the journey began, the Roman Empire wouldn't exist for another few centuries. When the journey ended, we'd be living in a world unrecognizably different from the one we left. And that's just the nearest star. Most stars are much, much farther away. The Milky Way galaxy, our home galaxy, is about 100,000 light-years across. That means light takes 100,000 years to cross from one edge to the other. If you started traveling at light speed from one side of the galaxy, by the time you reach the other side, 100,000 years would have passed. Human civilization, as we know it, has only existed for about 10,000 years. Agriculture was invented roughly 12,000 years ago. Writing appeared about 5,000 years ago. In 100,000 years, everything we recognize as human culture could be completely gone, replaced by something else entirely. And the Milky Way is just one galaxy. There are an estimated 2 trillion galaxies in the observable universe. The nearest large galaxy to us is Andromeda, about 2.5 million light-years away. If a civilization in Andromeda sent us a radio signal today, traveling at light speed, that signal wouldn't reach Earth for 2.5 million years. By the time we received it, our species might not even exist anymore. We might have evolved into something else, gone extinct, or spread across the stars in ways we can't currently imagine. And that's assuming the signal could even make the journey intact. Space isn't empty. It's filled with gas, dust, radiation, magnetic fields. A signal, traveling across 2.5 million light-years, would be scattered, absorbed, degraded. By the time it arrived, if it arrived, it might be so faint and distorted that we couldn't distinguish it from background noise. The interstellar medium, the thin gas that fills the space between stars, contains about 1 atom per cubic centimeter on average. That sounds empty, and compared to Earth's atmosphere, which contains about 10 to the power of 19 molecules per cubic centimeter, it basically is. But across light years, those scattered atoms add up. A radio signal, traveling from Andromeda to Earth, would pass through quintillions of cubic meters of this medium. Each interaction with an atom or molecule scatters a tiny bit of the signal's energy. Most passes through, but some gets absorbed or deflected. Over 2.5 million light-years, the cumulative effect is enormous. The signal spreads out, loses coherence, becomes noise. And that's just the gas. There's also dust, tiny grains of silicate and carbon molecules that formed in the atmospheres of dying stars or in the shock waves of supernovae. These dust grains are microscopic, but there are trillions upon trillions of them scattered throughout the galaxy. They absorb and scatter light, particularly shorter wavelengths. This is why distant stars look redder than they actually are. The blue light gets scattered away by dust, leaving mostly red light to reach us. The same thing happens to radio signals, though the effect varies depending on frequency. Then there's the plasma, ionized gas that exists in various concentrations throughout space. Plasma interacts with electromagnetic radiation in complex ways, bending and distorting signals. Near stars, where stellar winds blow ionized particles into space, the plasma density is higher and the effects more pronounced. In the space between galaxies, intergalactic space, the plasma is thinner but still present. And there's radiation, cosmic rays, high-energy particles from supernovae and other violent events constantly stream through space. Gamma rays from distant quasars and active galactic nuclei, X-rays from neutron stars and black holes. All of this adds noise to any signal you're trying to detect. It's like trying to have a conversation in a crowded, noisy room where everyone's shouting. Your signal is there, but it's buried under a cacophony of natural electromagnetic noise from countless sources throughout the universe. To detect an alien signal, you'd need to filter out all this noise, identify the pattern in the static, and prove that it's not just a natural phenomenon that happens to look artificial. That's extraordinarily difficult, even for signals from within our own galaxy. For signals from other galaxies, it's nearly impossible with current technology. This is the first and most fundamental barrier. Space is so incomprehensibly vast that even communication, even just sending a message, becomes almost impossible across galactic distances. The problems compound. Distance dilutes the signal. The interstellar medium scatters and absorbs it. Natural radiation creates noise that masks it. And time ensures that by the time a message arrives, the sender might be long gone. Even within our own galaxy, the challenges are immense. The Milky Way is 100,000 light-years across. A signal sent from one side to the other would take 100,000 years to arrive. That's not a communication network. That's sending messages to the distant future with no guarantee anyone will be there to receive them. And between galaxies? Forget it. The distances are so vast that communication becomes less like a conversation and more like archaeology. You're not talking to someone. You're finding traces of a civilization that existed millions of years ago, interpreting their message and sending a reply that won't arrive for millions of years more. By the time your reply reaches them, their entire evolutionary history from the point they sent the message could be complete. They could have evolved into a different species, colonized 100 worlds, collapsed into barbarism, or gone extinct. Your message would arrive at a world utterly transformed, where the original senders are as remote to the recipients as ancient Sumerians are to us. But distance is only part of the problem. There's another barrier, equally insurmountable: time. Even if we could somehow overcome the distance problem, even if we had faster-than-light travel or some other science fiction solution, we'd still face the fact that civilizations exist in time as well as space. They rise, they flourish, they decline, they disappear. And the windows during which any two civilizations might overlap are vanishingly small when measured against cosmic timescales. Let me put this in perspective. Earth formed about 4.54 billion years ago. For the first few 100 million years, it was a molten hellscape, bombarded by asteroids and comets, completely uninhabitable. The surface was liquid rock. The atmosphere was toxic, full of carbon dioxide, methane, ammonia, and water vapor. There were no oceans yet, because water couldn't exist as a liquid at those temperatures. The planet was being constantly reshaped by impacts, each large collision releasing enough energy to remelt the surface. The Moon formed during this period, about 4.5 billion years ago, when a Mars-sized object called Theia slammed into early Earth. The collision ejected enormous amounts of material into orbit, which eventually coalesced into the Moon. The impact was so violent that both Earth and Theia were completely destroyed and reformed from the debris. It took millions of years for Earth to cool enough for the surface to solidify into rock. It took millions more for water vapor in the atmosphere to condense and fall as rain, forming the first oceans. By about 4 billion years ago, Earth had cooled enough to have liquid water on its surface. This is when life could have begun. Life appeared relatively quickly after that, probably within a few 100 million years of Earth cooling enough to have liquid water. The oldest evidence we have for life comes from rocks in Western Australia and Greenland, dated to about 3.8 billion years ago. These rocks contain carbon isotope ratios that suggest biological activity. Specifically, they show an enrichment in carbon-12 relative to carbon-13, which is what happens when living organisms preferentially use carbon-12 in their metabolic processes. We also have structures called stromatolites, layered formations created by colonies of microbes, dating back to about 3.5 billion years ago. So life appeared early in Earth's history, within the first billion years. And then, for over 3 billion years, life remained simple. Just bacteria and archaea, single cells doing their thing, evolving slowly but never developing complexity. These microbes were incredibly successful. They filled every available niche. They evolved photosynthesis, learning to capture energy from sunlight. They developed metabolic pathways that could extract energy from chemicals like sulfur and iron. They created the first ecosystems, complex webs of organisms living off each other's waste products. But they remained single cells. No tissues, no organs, no specialized structures beyond the cellular level. It wasn't until about 2 billion years ago that cells developed internal structures, becoming what we call eukaryotic cells. These are more complex cells with a nucleus and other specialized components like mitochondria and chloroplasts. The development of eukaryotic cells was a major evolutionary leap. It probably happened through a process called endosymbiosis, where one cell engulfed another but didn't digest it. Instead, the engulfed cell became a permanent resident, eventually evolving into an organelle. Mitochondria, the powerhouses of the cell, were probably once free living bacteria that got incorporated into another cell. Chloroplasts, which perform photosynthesis in plant cells, were probably once cyanobacteria. But even after eukaryotic cells appeared, life remained mostly single-celled for another billion years. Multicellular life didn't appear until about 600 million years ago. Before that, Earth was covered in microbial mats and simple colonies, but nothing you'd recognize as an animal or plant. The Ediacaran period, from about 635 million to 541 million years ago, saw the first complex multicellular organisms. These were weird creatures, unlike anything alive today. Flat, quilted things that lay on the seafloor. Strange frond-like forms that might have been animals or fungi or something else entirely. We don't fully understand what they were or how they relate to modern life. Many of them went extinct before the Cambrian explosion. The Cambrian explosion, when complex animal life suddenly diversified into many different forms, happened about 540 million years ago. This is when most of the major groups of animals appeared. Trilobites, the iconic fossils from the Cambrian, were already sophisticated creatures with jointed legs, compound eyes, and complex behaviors. Anomalocaris, a predator over 1/2 meter long, hunted in Cambrian seas. Early chordates, the ancestors of all vertebrates, including us, appeared as small eel-like creatures. In just a few tens of millions of years, a blink in geological time, life went from mostly simple and small to complex and diverse. But this happened more than 500 million years after Earth formed. It took billions of years to get from single cells to complex animals. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. They dominated Earth for over 160 million years, far longer than mammals have been the dominant land animals. And during all that time, no dinosaur developed intelligence comparable to humans. Some were probably quite smart, relatively speaking. Troodon, a small predatory dinosaur, had a brain-to-body ratio similar to modern birds, which are quite intelligent. But none of them built cities or developed technology. Modern humans, Homo sapiens, appeared only about 300,000 years ago. For most of that time, we lived as hunter-gatherers, in small groups, without agriculture or permanent settlements. Civilization, with agriculture and cities and writing, is less than 10,000 years old. The first cities appeared in Mesopotamia around 5,500 years ago. Writing developed around 5,000 years ago, also in Mesopotamia, though other writing systems developed independently in Egypt, China, and Mesoamerica. Industrial technology is less than 300 years old. The Industrial Revolution, when we started using machines powered by fossil fuels, began in the late 1700s in Britain and spread from there. Radio communication, the ability to send signals across space, is barely over 100 years old. Guglielmo Marconi sent the first radio signals across the Atlantic in 1901. So out of Earth's 4.54 billion year history, we've only been capable of interstellar communication for the last 125 years or so. That's 0.0000275% of Earth's existence. Less than 0.03%. A microscopic sliver of time so brief, it's almost meaningless on geological scales. If you compressed Earth's history into a single 24-hour day, with Earth forming at midnight, life would appear around 4 in the morning. Multicellular life wouldn't show up until about 8:30 in the evening. Dinosaurs would appear at about 10:45 at night and go extinct at about 11:40. Modern humans would appear in the last few seconds before midnight. All of recorded human history, from the first Sumerian cities to today, would happen in the last 1/10 of a second. Our entire technological civilization, from the Industrial Revolution to now, would happen in the last few thousandths of a second. And our ability to communicate with other stars. That would have begun in the last millionth of a second before midnight. That's how recent we are. That's how brief our communicative window has been so far. Now think about what happens in the future. How long will human civilization last? We don't know. Maybe another 100 years before we destroy ourselves through climate change or nuclear war or some other catastrophe. Maybe 1,000 years. Maybe 10,000. If we're incredibly lucky and careful, maybe 1,000,000 years. But even 1,000,000 years is nothing compared to geological and cosmic timescales. Stars last billions of years. Galaxies last tens of billions. The universe is already about 13.8 billion years old and will likely continue for trillions of years in some form. On these timescales, 1,000,000-year civilization is a brief flicker, here and gone. Now imagine another planet with intelligent life. They go through the same process. Their planet forms, life emerges, evolution proceeds, intelligence develops, technology appears. But the timing is different. Maybe their planet formed 1 billion years before Earth. Their civilization rose and fell long before life on Earth even became multicellular. By the time humans appeared, they were already extinct, their ruins eroded, their signals long since faded into the cosmic background radiation. Or maybe their planet formed 1 billion years after Earth. Their civilization won't emerge until long after our sun has died, until Earth is a cold, dead rock orbiting a white dwarf star, all traces of humanity erased. We'd never know they existed. They'd never know we existed. 2 ships passing in the night, separated by 1 billion years of time, and 1 billion years is actually a relatively short separation. Planets could form 10 billion years apart and both produce intelligent life, but never overlap in their communicative windows. This is the temporal problem. Even if intelligent civilizations are common, even if every galaxy contains thousands or millions of them, the chances that any two exist at the same time and are both capable of communication is incredibly small. It's like trying to coordinate a meeting between two people who are both wandering randomly through a vast city, neither knowing when or where the other will be, with no way to communicate or plan. The odds of them bumping into each other by pure chance are essentially zero. Let's talk about the speed of light. In science fiction, this is usually treated as an engineering problem. Ships have faster-than-light drives, wormholes, hyperspace, subspace, any number of fictional workarounds that let characters zip across the galaxy in hours or days. But in reality, the speed of light isn't just a speed limit. It's a fundamental feature of how the universe works. It's woven into the fabric of space-time itself. Light travels at about 186,000 miles per second in a vacuum. This speed isn't arbitrary. It falls directly out of the equations of electromagnetism, discovered by James Clerk Maxwell in the 1860s. Maxwell showed that electricity and magnetism are aspects of the same fundamental force, and that electromagnetic waves, including light, must propagate at a specific speed determined by the properties of empty space. When Maxwell calculated what that speed should be based on measurements of electric and magnetic forces, he got a number very close to the measured speed of light. This wasn't a coincidence. It was proof that light is an electromagnetic wave. But Maxwell's equations work in any reference frame, which created a puzzle. If you're standing still and you measure the speed of light, you get 186,000 miles per second. If you're moving toward a light source, common sense says you should measure a higher speed, your speed, plus the light speed. If you're moving away, you should measure a lower speed. But experiments showed that's not what happens. Everyone measures the same speed of light, regardless of how they're moving. This makes no sense in classical physics. It only makes sense if you accept that space and time are not absolute. That's what Einstein figured out in 1905 with his special theory of relativity. He proposed that the speed of light is constant in all reference frames, and that space and time must adjust to make this work. If you're moving fast, time slows down for you, and distances contract in the direction of motion. These aren't optical illusions or measurement errors. Time really does pass more slowly for you, and distances really do contract. This has been confirmed by countless experiments. Particles called muons are created when cosmic rays hit Earth's atmosphere about 9.3 miles up. Muons are unstable and decay in about 2 microseconds, 2 millionths of a second. Even traveling at nearly the speed of light, they should only make it about a third of a mile before decaying. They shouldn't reach the ground. But they do reach the ground in large numbers. Why? Because from our perspective, time is passing slowly for the muons, so they last longer than 2 microseconds. From the muons' perspective, the distance to the ground is contracted, so they don't have as far to travel. Either way, the effect is real and measurable. GPS satellites have to account for relativistic time dilation. They're moving fast relative to Earth's surface, and they're in a weaker gravitational field, both of which affect how fast time passes for them. If GPS systems didn't correct for these effects, they'd accumulate errors of about 6 miles per day, making them useless for navigation. So relativity isn't theoretical. It's a practical fact we deal with in everyday technology. And one of the consequences of relativity is that nothing with mass can reach the speed of light, let alone exceed it. As an object with mass accelerates toward light speed, it requires more and more energy to continue accelerating. The closer you get to light speed, the more energy you need. To actually reach light speed would require infinite energy. And since infinite energy doesn't exist, objects with mass cannot reach light speed, let alone exceed it. This isn't like the sound barrier, where you just need a more powerful engine. This is a fundamental limit built into the structure of reality. Some people have proposed theoretical workarounds. Alcubierre drives, warp drives that bend space-time around a ship, contracting space in front and expanding it behind, allowing the ship to effectively move faster than light without technically violating relativity. The ship itself doesn't move through space faster than light. Instead, space moves around the ship. It's like standing on a moving walkway at an airport. You're walking at normal speed, but the walkway carries you faster than you could walk alone. The Alcubierre drive would work similarly, creating a bubble of space-time that moves, carrying the ship with it. This is mathematically possible within the framework of general relativity. Einstein's equations allow it. But there are enormous practical problems. First, you need something called exotic matter, matter with negative energy density. We've never observed anything like this. Quantum field theory predicts that negative energy densities can exist under certain conditions, like in the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force because certain wavelengths of virtual particles can't exist between the plates. This creates a region of slightly negative energy density. But the amounts are tiny, and we don't know how to create large amounts of exotic matter. Second, even if you had exotic matter, the amounts required would be enormous. Early calculations suggested you'd need the mass-energy equivalent of the entire visible universe. Later refinements brought this down somewhat, but you'd still need something on the order of the mass of Jupiter, converted entirely into exotic matter. That's not happening with any technology we can envision. Third, there are causality problems. Faster-than-light travel creates situations where cause and effect can be reversed. You can arrive before you leave, creating grandfather paradoxes and other logical impossibilities. Some physicists argue this means nature must forbid faster-than-light travel, even if the equations technically allow it. Wormholes are another proposed workaround. A wormhole is a tunnel through space-time connecting two distant points. Instead of traveling the long way around through normal space, you take a shortcut through the wormhole. Again, this is mathematically possible in general relativity. The equations allow solutions that include wormholes. But again, stabilizing a wormhole requires exotic matter. Without it, the wormhole would collapse instantly, faster than anything could travel through it. And even if you could stabilize one, you'd still have causality problems. Traveling through a wormhole is equivalent to traveling backward in time in certain reference frames, which creates all the same paradoxes as faster-than-light travel. There are other ideas. Quantum entanglement, where particles become correlated such that measuring one instantly affects the other, regardless of distance. But you can't use entanglement to send information faster than light. The correlation is there, but you can't control it in a way that transmits a message. Every attempt to exploit entanglement for communication runs into the same problem. The information still can't travel faster than light. So, for all practical purposes, we're stuck with light speed as an absolute limit. Not because we haven't figured out the trick yet, but because the universe is fundamentally structured this way. And that creates profound consequences for interstellar travel and communication. If you want to send a probe to another star system, it will take years, at minimum, likely decades or centuries. The fastest human-made object ever to leave the solar system is Voyager 1. Launched in 1977, it's been traveling for nearly 50 years now. It's currently about 14.5 billion miles from Earth, well beyond the orbit of Pluto, in interstellar space. And it's moving at about 38,000 miles per hour relative to the Sun. That sounds fast, and by human standards it is. It's about 48 times faster than a bullet from a high-powered rifle. But in cosmic terms, it's crawling. At that speed, Voyager 1 would take over 73,000 years to reach Proxima Centauri. If it were headed in that direction, which it's not, it's actually heading toward a star called AC plus 79 3888 in the constellation Camelopardalis. It'll pass within about 1.6 light-years of that star in about 40,000 years. The New Horizons probe, which flew past Pluto in 2015, is traveling even faster, about 36,000 miles per hour relative to Earth, though its velocity relative to the Sun varies depending on its trajectory. At its current speed, it would also take tens of thousands of years to reach the nearest stars. Now, these probes weren't designed for interstellar travel. They were designed to study planets in our solar system. The fact that they're leaving the solar system at all is almost incidental. We could, in theory, design a probe specifically for interstellar travel optimized for speed. Several proposals have been made over the years. Project Daedalus, designed in the 1970s by the British Interplanetary Society, was a theoretical fusion-powered spacecraft that could reach 12% the speed of light. At that speed, it could reach nearby stars in about 30 to 40 years. The design called for a two-stage spacecraft using nuclear fusion for propulsion. The fuel would be a mixture of deuterium and helium-3, isotopes that can be fused together to release enormous amounts of energy. The spacecraft would accelerate for about 4 years, burning through hundreds of thousands of tons of fuel, then coast for the rest of the journey. It would carry scientific instruments and cameras to study the target star system as it flew past at relativistic speeds. But here's the problem. Daedalus was never built because the engineering challenges are enormous. You need hundreds of thousands of tons of fuel, most of which doesn't exist in accessible form on Earth. Helium-3 is rare on our planet. You'd have to mine it from the atmospheres of gas giants like Jupiter or Saturn, which presents its own set of impossible challenges. You need fusion reactors that can operate continuously for years, something we haven't achieved even for stationary power plants on Earth. You need materials that can withstand the intense heat and radiation of the fusion reaction. You need to accelerate smoothly enough that delicate instruments aren't destroyed, but powerfully enough to reach 12% light speed in 4 years. And after all that, the probe would fly through the target system in a matter of hours or days, gathering data, then continue into interstellar space with no way to stop or return. The Breakthrough Starshot Initiative, announced in 2016, proposes a different approach. Instead of carrying fuel, the spacecraft would be tiny, weighing only a few grams, with a large, ultra-thin, light sail. Ground-based lasers would blast the sail with intense beams of light, accelerating the tiny craft to about 20% the speed of light. At that velocity, it could reach Proxima Centauri in about 20 years. The idea is elegant. No fuel to carry means the spacecraft can be much lighter. The acceleration happens near Earth, where we have power available, rather than carrying power sources into space. Multiple probes could be launched cheaply, increasing the chances of success. But again, the engineering challenges are immense. You need lasers with a combined power output of about 100 gigawatts, roughly the output of 100 large nuclear power plants, all focused into a tight beam aimed at a sail a few meters across. The sail has to be incredibly thin, maybe a few hundred atoms thick, but strong enough to withstand the intense laser light without vaporizing. The spacecraft has to carry instruments, cameras, and a transmitter, all weighing just a few grams total, and they have to survive 20 years in the harsh environment of space. And at 20% light speed, even tiny dust grains become devastating projectiles. A grain of sand hitting the spacecraft would release energy equivalent to a large bomb. The craft would need shielding, which adds weight, which requires more laser power, which makes the whole system harder to build. And when it arrives at Proxima Centauri, it'll be moving so fast that it can only observe the system for a few hours before flying past and continuing into deep space. There's no way to slow down. Even if we solve all these problems, even if we build a working interstellar probe using lasers or fusion or some other technology, the timescales are still daunting. A 20-year flight to Proxima Centauri sounds manageable. Launch the probe today. Receive data back 40 years from now, accounting for the light speed delay for the signal to return. That's within a human lifetime. The people who launched the mission might still be alive when the first images arrive. But Proxima Centauri is the nearest star. What about more interesting targets? Tau Ceti, a sun-like star 12 light-years away, is often mentioned in discussions of habitable planets. At 20% light speed, a probe would take 60 years to arrive. Add 12 years for the signal to return, and you're looking at 72 years total. The scientists who launched the mission would be retired or gone. The next generation would receive the data. Epsilon Eridani, another nearby sun-like star, is 10.5 light-years away. About the same timeline. For stars 20, 30, or 50 light-years away, the timescales become generational. You launch a probe for your grandchildren or great-grandchildren to benefit from. The institutional continuity required is extraordinary. Governments change. Funding priorities shift. Entire space agencies could be disbanded and reformed in the time it takes for a mission to complete. Look at history. The Apollo program landed humans on the Moon in 1969, then was cancelled just 3 years later. We haven't been back with humans since 1972, over 50 years ago. Political will evaporates. Budgets get cut. Priorities change. Now, imagine trying to maintain funding and institutional support for a mission that won't return data for 70 years. It's almost inconceivable. No politician wants to fund a project that won't show results during their career. No space agency wants to commit resources to something that won't produce returns for 3 generations. The incentives all point towards short-term projects with clear timelines and measurable outcomes. Interstellar missions don't fit that model. Even if we could build the technology, Even if we could afford it, the political and institutional barriers might be insurmountable. For more distant stars, the timescales become absurd. A star 50 light-years away would require 500 years minimum for a probe traveling at 10% light speed to arrive and send back a signal. That's longer than the United States has existed as a country. Longer than most civilizations last. You'd be launching a mission for your descendants, not for yourself, and they'd be receiving results meant for their descendants, not for themselves. No individual, no government, no organization would fund a mission with a 500-year timeline. The incentives don't work. The people making the decision would be dead long before any results came back. The society that launched the mission might not even exist anymore by the time the data arrived. This is why interstellar travel, while not physically impossible, is practically impossible for any civilization remotely like ours. The timescales are too long. The distances are too vast. The energy requirements are too high. And the benefits are too uncertain. Let's assume, for the sake of argument, that some civilization overcomes all these problems. They develop technology that allows them to travel at a significant fraction of light speed, maybe 10 or 20%. They build generation ships, enormous vessels where multiple generations live and die during the journey to another star. Or they develop suspended animation, freezing travelers in some kind of stasis until they arrive. Or they send AI-controlled probes that don't need life support. Any of these approaches could work, in theory. They're all technically possible, given enough time and resources. So, let's say this civilization starts exploring nearby stars. They send out ships, probes, signals. They spread across their local region of the galaxy, establishing colonies, or at least listening posts on planets orbiting nearby stars. Over thousands or millions of years, they expand, slowly, painfully, but steadily. Eventually, they might control a sphere of influence hundreds or thousands of light years across. Now, here's the question. If a civilization can do this, why haven't we seen any evidence of it? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked at lunch one day, in 1950, "Where is everybody?" The story goes that Fermi and colleagues were discussing recent UFO reports and the possibility of faster-than-light travel. Someone remarked that if advanced civilizations exist and have faster-than-light travel, they should be visiting Earth. Fermi did some quick mental calculations about how long it would take a spacefaring civilization to colonize the galaxy, even at sublight speeds, and concluded they should have done so already. Then he asked his question: where is everybody? If the galaxy is old enough and big enough for intelligent life to have emerged many times, and if such life tends to spread and colonize, we should see evidence of it. But we don't. The paradox is this. The universe is very old, about 13.8 billion years. The Milky Way galaxy formed over 13 billion years ago. Stars and planets have been forming for most of that time. Earth is only 4.54 billion years old. There are stars in the Milky Way that are over 12 billion years old, more than twice Earth's age. Planets around those stars could have formed billions of years before Earth. Life could have started there billions of years earlier. Civilizations could have risen and developed technology when Earth was still a molten ball of rock. There's been plenty of time for intelligent life to emerge, develop technology, and spread across the galaxy. Even at sublight speeds, a civilization could colonize the entire Milky Way in a few tens of millions of years. Here's how that math works. Suppose a civilization develops interstellar travel and starts sending colony ships to nearby stars. Each journey takes, say, 100 years at 10% light speed. The colony ship arrives, settles on a planet, establishes a self-sustaining population. After a few hundred years, that colony is stable and prosperous enough to send out its own colony ships. So, every few hundred years, each colony spawns new colonies. This is exponential growth. Start with one colony. After a few hundred years, you have 3 or 4 colonies. Each of those sends out more ships. So a few hundred years later, you have dozens. Then hundreds. Then thousands. The number grows exponentially, doubling every few hundred years. At that rate, you could fill a galaxy in a surprisingly short time. The Milky Way contains about 200 billion stars, but most of them are clustered in a disk about 100,000 light-years across. If you're growing exponentially, sending colonies in all directions, it doesn't matter that there are billions of stars. You don't need to visit every star. You just need to fill the volume of space. Calculations suggest that even with conservative assumptions, slow ships, long pauses between sending new colonies, you could colonize a galaxy the size of the Milky Way in somewhere between 5 million and 50 million years. Let's say 50 million years to be very conservative. That's long by human standards, but it's less than 0.5% of the galaxy's age. If intelligent life appeared anywhere in the Milky Way, even 1 billion years ago, they've had plenty of time to spread everywhere. So where are they? Why don't we see evidence of advanced civilizations everywhere? We should see signs. Megastructures built around stars to capture energy, like Dyson spheres or Dyson swarms. Terraformed planets with atmospheric compositions that don't occur naturally. Radio signals, either intentional broadcasts or just the accidental leakage of a technological civilization's communications. Artifacts left behind on planets or moons. Probes exploring the galaxy, like our Voyager spacecraft, but far more advanced. We should see something, but we don't. The galaxy appears to be empty. As far as we can tell, there's no evidence of any advanced technological civilization besides us. This is the Fermi paradox. The apparent contradiction between the high probability that alien civilizations exist and the complete lack of evidence for them. There are many proposed solutions to the Fermi paradox, and they generally fall into a few categories. First, maybe intelligent life is incredibly rare. Maybe the jump from non-life to life is much harder than we think. On Earth, life appeared quickly once conditions allowed, but maybe Earth is an outlier. Maybe the chemistry that produces self-replicating molecules almost never happens. Or maybe the jump from single-celled organisms to multicellular life is the hard part. On Earth, it took 2 billion years, which suggests it's not easy. Maybe on most planets, life gets stuck at the bacterial stage and never progresses. Or maybe the development of intelligence is a fluke that happened on Earth but almost nowhere else. Intelligence is expensive. It requires large brains, which consume enormous amounts of energy. A human brain is about 2% of body weight, but uses about 20% of the body's energy. That's a huge investment that only pays off if intelligence provides enough survival advantage to justify the cost. On Earth, intelligence evolved in response to specific selection pressures, social competition, tool use, complex environments. Maybe those conditions are rare. Maybe on most planets with life, evolution never produces intelligence because the environmental conditions don't favor it. Second, maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. This is sometimes called the Great Filter. The idea is that there are one or more extremely difficult steps in the path from non-life to spacefaring civilization, and most attempts fail. Maybe the filter is behind us, something like the origin of life or the development of multicellular organisms, in which case we're lucky to have made it this far. Or maybe the filter is ahead of us. Maybe civilizations that develop nuclear weapons and other destructive technologies almost always destroy themselves before they can spread to other stars. We've come close several times. The Cuban Missile Crisis in 1962 brought the US and Soviet Union to the brink of nuclear war. There have been false alarms, where early warning systems detected incoming missiles that didn't exist. In some cases, the decision not to launch a retaliatory strike came down to the judgment of a single person. We got lucky. Maybe most civilizations don't. Maybe the window between developing radio technology and self-destruction is only a century or two. That would explain why we don't see evidence of alien civilizations. They exist, but they don't last long enough to become visible on cosmic scales. They flicker into existence, burn brightly for a brief moment, and then vanish, leaving no trace. Third, maybe advanced civilizations choose not to colonize or communicate. For reasons we don't understand, maybe they develop technology but have no interest in space. Maybe they turn inward, focusing on virtual realities or other pursuits that don't require physical expansion. Maybe they deliberately hide, staying quiet to avoid drawing attention. This is the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin. The idea is that the galaxy is like a dark forest at night. There might be other hunters out there, but everyone stays silent and hidden because making noise reveals your position and makes you a target. Maybe contact between civilizations always goes badly for one or both parties. Maybe competition for resources leads to conflict. Maybe advanced civilizations have learned this through bitter experience and now follow a policy of silence. They listen, but they don't broadcast. They watch, but they don't reveal themselves. And so, the galaxy remains silent, not because it's empty, but because everyone is hiding. Fourth, and this is what we're focusing on tonight, maybe civilizations are out there, but they're all so far apart that none of them have ever encountered another. Even if intelligent life is common, the sheer scale of space and time makes contact extraordinarily unlikely. This isn't saying civilizations are rare. It's saying that, even if they're common by cosmic standards, space is so vast that common still means incredibly isolated. Let's do some math. The Milky Way contains somewhere between 100 billion and 400 billion stars. Let's use 200 billion as a round number. If even 1% of those stars have planets, that's 2 billion planetary systems. If 1% of those have habitable planets, that's 20 million habitable worlds. If 1% of those develop life, that's 200,000 planets with life. If 1% of those develop intelligent life, that's 2,000 civilizations in the Milky Way right now. 2,000 intelligent species, scattered across a galaxy 100,000 light-years across. Sounds like a lot, right? But let's think about the spacing. If you distribute 2,000 civilizations evenly across the Milky Way, each one is, on average, separated from its nearest neighbor by about 500 light-years. 500 light-years. That's the distance light travels in 500 years. A radio signal from one civilization wouldn't reach the other for 500 years. A response wouldn't come back for another 500 years. 1,000-year round trip for a single exchange of information. And that's assuming they're both broadcasting and listening at the same time, using the same frequencies in the right direction, with enough power for the signal to be detectable. It assumes a lot of things going right. In reality, the odds are much worse. Civilizations might exist for only a brief window of time. Maybe they only broadcast for a few hundred years before going extinct or losing interest. If your civilization's communicative window is only 200 years, and your nearest neighbor is 500 light-years away, you might send out signals for 2 centuries and never receive a reply, simply because the signal hasn't arrived yet when you stop broadcasting. Or their signal reaches you after your civilization has collapsed. The timing has to line up perfectly. Both civilizations have to exist at the same time. Both have to be broadcasting. Both have to be listening. Both have to be using compatible technology. Both have to be pointing in the right direction. The signal has to be strong enough to be detected across hundreds of light-years. And even if all of that happens, communication is agonizingly slow. Every exchange takes a millennium. You couldn't have a conversation. You couldn't negotiate. You couldn't even confirm that the other civilization still exists by the time you receive their message. You'd be communicating with ghosts, echoes, from a society that might be long gone. Let's make this even more concrete. Imagine Earth starts broadcasting radio signals in the year 1900. That's roughly when we developed radio technology. Those signals spread out in all directions at the speed of light, forming an expanding sphere. By the year 2026, that sphere has a radius of 126 light-years. Any star within 126 light-years of Earth could, in principle, have detected our radio signals by now. How many stars is that? Within 126 light-years of Earth, there are roughly 2,000 stars, give or take. That's out of 200 billion stars in the galaxy. Our signals have reached 0.0001% of the Milky Way's stars. Now, imagine one of those 2,000 stars has a planet with intelligent life. They detect our signal in, say, the year 2000. They're excited. They're not alone. They immediately send a response. That response travels at light speed. If they're, say, 100 light-years away, their response would reach Earth in the year 2100. By that time, everyone who was alive when we first started broadcasting is gone. The world has changed in ways we can't predict. Maybe we've stopped listening for alien signals. Maybe our civilization has collapsed. Maybe we've moved on to other things. Or maybe we're still listening, still hopeful, and we receive their message. We decode it. We celebrate. We send a response. That response won't reach them until the year 2200. By then, it's been 200 years since they first detected us. Will their civilization still exist? Will they still care? Will they even remember that they sent a message to us? This is the tyranny of distance, combined with the speed of light. It turns conversation into something more like archaeology. You're not talking to living beings. You're exchanging messages with the past and the future. Every message is a time capsule, sent in hope that someone will still be around to receive it. There's another problem we haven't discussed yet: energy. Sending signals across interstellar distances requires enormous amounts of power. Radio waves, like all electromagnetic radiation, obey the inverse square law. As they travel away from their source, they spread out, and their intensity decreases proportional to the square of the distance. Double the distance, and the signal becomes 1/4 as strong. Triple the distance, 1/9 as strong. By the time a radio signal has traveled 100 light years, it's been diluted by a factor of about 10 to the power of 33. That's a 1, followed by 33 zeros. The signal becomes unimaginably faint. To detect it, you need enormous radio telescopes and extremely sensitive receivers. And even then, you're competing with background noise from natural sources. Stars emit radio waves. Gas clouds emit radio waves. The cosmic microwave background, the afterglow of the Big Bang, produces a faint hiss across all frequencies. An alien signal, by the time it reaches us, might be so weak that it's drowned out by this natural noise. To overcome this, you'd need to broadcast with incredible power. Not the few kilowatts of a typical radio station, but megawatts or even gigawatts. That's the output of a large power plant dedicated entirely to sending a signal that might never be received. And you'd need to do it continuously, for years or decades or centuries, because you don't know when someone might be listening. It's an enormous investment with no guaranteed return. Most civilizations probably wouldn't bother. Why spend vast resources on a project that might produce no results for hundreds or thousands of years? The same problem applies to travel. To send a spacecraft to another star, you need to accelerate it to a significant fraction of light speed. The kinetic energy of an object is 1/2 mass times velocity squared. As velocity increases, energy requirements increase dramatically. To accelerate a spacecraft weighing 1,000 kilograms to 10% the speed of light, you'd need about 4.5 times 10 to the power of 17 joules of energy. That's roughly the total energy output of a large power plant running for several years. And that's just for a 1,000 kilogram spacecraft. A ship large enough to carry humans, with life support, supplies, and equipment, would weigh vastly more. You'd need energy equivalent to a significant fraction of your civilization's total output. And then you'd need to decelerate when you arrive. That requires just as much energy. So the total energy budget for a round-trip interstellar mission is staggering. It's not impossible, but it's incredibly expensive. Again, you have to ask, why would a civilization invest so much for such uncertain returns? Unless they're desperate, fleeing a dying star or a collapsing ecosystem, the incentive isn't there. Here's a thought that might make the isolation even worse. What if the physics we understand is incomplete, but not in a helpful way? What if there are barriers we don't even know about yet? For example, we know that space isn't truly empty. It's filled with virtual particles, quantum fluctuations, dark matter, dark energy. We don't fully understand any of these things. What if dark matter interacts with fast-moving objects in ways we haven't discovered? What if traveling at high speeds through regions of space with high dark matter density creates drag or radiation that damages spacecraft? What if the interstellar medium, the thin gas and dust between stars, becomes a significant hazard at relativistic speeds. A single dust grain, impacting a ship traveling at 20% light speed, would hit with the energy of a large bomb. You'd need shielding, lots of it, which adds mass, which requires more energy to accelerate. Maybe there are fundamental engineering limits we haven't encountered yet, because we've never tried to build anything that operates under those conditions. Maybe the universe is even less friendly to interstellar travel than we currently believe. Or, consider this. What if intelligence itself is the filter? What if civilizations that develop advanced technology inevitably create existential risks that they can't manage? Nuclear weapons, biological warfare, artificial intelligence, nanotechnology, climate change. Any of these could wipe out a civilization. And once you develop the capability to create these threats, you're in a race against time. Can you develop the wisdom and the social structures to manage these technologies before they destroy you? Maybe most civilizations fail that test. Maybe the window between developing radio technology and self-destruction is only a century or two. That would explain why we don't see evidence of alien civilizations. They exist, but they don't last long enough to become visible on cosmic scales. They flicker into existence, burn brightly for a brief moment, and then vanish, leaving no trace. If that's the case, then the universe might be filled with ruins, dead worlds, silent cities, technologies left to decay because their creators are gone. We might be surrounded by the graveyards of civilizations that came before us and fell to the same traps we're currently facing. Let's talk about the Drake equation. This is a famous formula proposed by astronomer Frank Drake in 1961 as a way to estimate the number of active, communicative civilizations in the Milky Way. It was developed for the first SETI conference, the Search for Extraterrestrial Intelligence, held in Green Bank, West Virginia. The equation was meant as a framework for discussion, a way to organize thinking about the problem rather than a tool for getting precise answers. It looks like this. N equals R star times F P times N E times F L times F I times F C times L. Let me break down what each term means. N is the number we're trying to calculate, the number of civilizations in the Milky Way that we might be able to detect right now. R star is the rate of star formation in the galaxy, measured in stars per year. We have pretty good estimates for this. The Milky Way forms about 1.5 to 3 stars per year on average, though the rate was higher in the past and is gradually declining. Fp is the fraction of stars that have planets. When Drake first proposed the equation, we didn't know the answer to this. But thanks to the Kepler Space Telescope and other planet-hunting missions, we now know that planets are extremely common. Essentially, every star has at least one planet on average. So, Fp is probably close to 1, maybe even slightly higher than 1 since many stars have multiple planets. Ne is the number of planets per star that could support life. This is trickier. We're talking about planets in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. Too close, and water boils away. Too far, and it freezes. For a sun-like star, the habitable zone is roughly where Earth is, from about 0.95 to 1.37 astronomical units from the star. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. Larger, brighter stars have habitable zones farther out. Smaller, dimmer stars have them closer in. Studies based on Kepler data suggest that about 20 to 40% of Sun-like stars have a planet in the habitable zone. For red dwarf stars, which are much more common than Sun-like stars, the fraction might be even higher, perhaps 50% or more. So NE might be 0.2 to 0.5 or so. But here's where things get uncertain. FL is the fraction of those habitable planets where life actually develops. We have exactly one data point for this: Earth. Life appeared on Earth very quickly, within a few 100 million years of the planet cooling enough to have liquid oceans. That suggests it might be easy. The raw materials for life, amino acids, nucleotides, sugars, are found in space. They've been detected in meteorites and in interstellar clouds. The chemistry that produces these molecules happens naturally. So maybe, once you have a habitable planet with liquid water and the right chemistry, life is almost inevitable. Or maybe Earth got incredibly lucky. Maybe the probability is 1 in a million or 1 in a billion, and we just happen to be the rare case where it worked. We don't know. There's no way to know without finding life elsewhere or understanding the origin of life well enough to calculate the probability from first principles. And we're nowhere near that level of understanding. Fi is the fraction of life-bearing planets where intelligent life evolves. Again, we have one data point: Earth. On Earth, it took over 3 billion years to go from single cells to multicellular life, and another 500 million to develop intelligence. Intelligence required a very specific evolutionary path. Our ancestors were tree-dwelling primates who developed grasping hands and stereoscopic vision for navigating branches. They came down from the trees and became bipedal, freeing their hands for tool use. They developed larger brains, probably driven by social competition within groups. They developed language, possibly as a side effect of brain structures used for other purposes. Each of these steps was contingent on specific environmental conditions and evolutionary pressures. If you rewind Earth's history and let evolution run again, would you get intelligence? Maybe. Maybe not. Some evolutionary biologists argue that something like intelligence is likely to evolve eventually on any planet with complex life, because it provides such a huge survival advantage. Others argue that intelligence is a rare fluke, the result of specific circumstances that might not be repeated elsewhere. We don't know. FC is the fraction of intelligent species that develop technology capable of interstellar communication. On Earth, that's us. But there are other intelligent species. Dolphins, whales, elephants, great apes, crows, octopuses, and others all show varying degrees of intelligence. None of them have built radios. Why did humans develop technology and not other intelligent species? Partly because we have hands capable of fine manipulation. Dolphins are intelligent, but lack appendages for building tools. Partly because we're social and can accumulate knowledge across generations through language and culture. Other animals have culture to some degree, but not to the extent humans do. Partly because we happen to evolve in environments that rewarded tool use. Our ancestors needed tools to hunt, to process food, to survive in diverse environments. Would an intelligent species on an ocean world develop technology? Maybe not, if they have everything they need in their aquatic environment. Would an intelligent species in a very stable, unchanging environment develop technology? Maybe not, if there's no pressure to innovate. So even if intelligence is common, technology might not be. The last term, L, is perhaps the most uncertain and most important. L is the length of time such civilizations remain detectable. How long does a technological civilization last? Humans have been capable of radio communication for about 125 years. Will we last another 100? Another 1,000? Another million? Nobody knows. Some civilizations might destroy themselves quickly. Nuclear war, biological weapons, runaway climate change, artificial intelligence that gets out of control. There are many ways a technological civilization could collapse or go extinct. If the average lifetime of a communicative civilization is only a few hundred years, then L is small, and N is very small. At any given moment, only a handful of civilizations might be broadcasting, and they'd be so spread out in space and time that they'd never encounter each other. On the other hand, if civilizations typically last millions of years, then L is large, and N could be large too. The galaxy could be full of signals we just haven't detected yet. The Drake equation doesn't give us an answer. It gives us a framework for thinking about the problem. And what it reveals is how many unknowns there are, how many ways the universe could be structured such that intelligent life is common, but contact is impossible. Let's plug in some numbers and see what we get. Conservative estimate. R star equals 2 stars per year. FP equals 1. Almost all stars have planets. NE equals 0.2. 1 in 5 stars has a habitable planet. FL equals 0.1. 1 in 10 habitable planets develops life. FI equals 0.1. 1 in 10 life-bearing planets develops intelligence. FC equals 0.1. 1 in 10 intelligent species develops technology. L equals 500 years. Civilizations last 5 centuries in a communicative state. Multiply it out. N equals 2 times 1 times 0.2 times 0.1 times 0.1 times 0.1 times 500. N equals 0.2 civilizations. That means, on average, at any given time, there's a 20% chance of one technological civilization existing in the galaxy. Most of the time, we're alone. Occasionally, there might be one other civilization out there, but we'd never know because they'd be thousands of light years away and exist at a different time. Optimistic estimate. R star equals 3 stars per year. FP equals 1. NE equals 0.5. Half of all stars have habitable planets. FL equals 1. Life appears on every habitable planet. FI equals 0.1. 1 in 10 life-bearing planets develops intelligence. FC equals 0.5. Half of intelligent species develop technology. L equals 10,000 years. Civilizations last 10,000 years in a communicative state. N equals 3 times 1 times 0.5 times 1 times 0.1 times 0.5 times 10,000. N equals 7,500 civilizations. That's a lot. If there are 7,500 civilizations in the Milky Way, and the galaxy is 100,000 light-years across, they're still spread out. On average, each civilization is separated from its nearest neighbor by about 300 light-years. 300 light-years is still an enormous distance. A radio signal takes 300 years to cross that gap. If a civilization broadcasts for 10,000 years total, and their nearest neighbor is 300 light-years away, the signal will reach that neighbor. But by the time a reply could arrive, 600 years have passed. If the receiving civilization responds immediately, and the original civilization is still listening, contact could be established. But the conversation would be agonizingly slow, each exchange taking 600 years. And this assumes both civilizations exist at the same time. Both are broadcasting, both are listening, both are using compatible technology, and both are interested in making contact. That's a lot of assumptions. In reality, even with 7,500 civilizations, contact might be extremely rare or non-existent. The point is, the Drake equation shows us that unless certain parameters are very favorable, the number of communicative civilizations could be very small. And even if the number is moderately large, the distances involved make contact difficult. Let's consider a specific scenario. Suppose there are 10,000 intelligent civilizations in the Milky Way right now. That's a generous estimate, much higher than most scientists would guess, but let's go with it. 10,000 civilizations, scattered randomly across a galaxy 100,000 light-years across. On average, each civilization is separated from its nearest neighbor by about 300 light-years. Now, suppose each civilization exists for 10,000 years. That's the length of human civilization so far, from the first agricultural settlements to today. During those 10,000 years, they might be capable of interstellar communication for, say, 500 years. Before that, they haven't developed the technology yet. After that, they either go extinct or stop broadcasting for some reason. So each civilization has a 500-year window when they're detectable. At any given moment, out of those 10,000 civilizations, only a small fraction are currently in their communicative window. If we assume civilizations are evenly distributed in time, which is a big assumption, but let's run with it, then at any given moment, maybe 500 of them are broadcasting. 500 civilizations out of 200 billion stars. Your nearest broadcasting neighbor is, on average, about 1,000 light-years away. A signal from them would take 1,000 years to reach you. If you send a reply, it takes another 1,000 years to get back. 2,000-year round trip. But remember, they're only broadcasting for 500 years. By the time your signal reaches them, they've been silent for 1,500 years. Your message arrives at a dead world, or at least a world that's no longer listening. They never know, you replied. You never hear from them again. In this scenario, the galaxy is full of civilizations, but they're all shouting into the void, their signals arriving at distant stars long after anyone is there to hear them. It's not that contact is unlikely. It's that the universe is structured in such a way that contact is almost impossible. There's one more barrier we should discuss: the nature of intelligence itself. We tend to assume that intelligence follows a certain pattern, that any intelligent species will be curious, will want to explore, will develop technology, will try to communicate. But what if that's wrong? What if intelligence takes forms we don't recognize? What if some civilizations develop technology but have no interest in space? Maybe they're ocean dwellers, living on a planet with a thick ice crust, completely unaware that a universe exists beyond their ocean. Maybe they're hive minds, with completely different motivations and priorities than individual-based consciousness. Maybe they're artificial intelligences, created by biological beings, but now existing independently, with goals we can't comprehend. Maybe they're post-biological, having uploaded themselves into some kind of virtual reality where they're perfectly happy and see no reason to interact with the physical universe. We're limited by our own experience. We know one example of intelligence, human intelligence, and we're extrapolating from that. But intelligence could take countless forms, most of which might have no interest in communicating with us, even if they could. There's also the possibility that communication is happening, but we don't recognize it. We're listening for radio signals because that's what we use. But an advanced civilization might communicate using something we haven't discovered yet. Maybe they use neutrinos, which can pass through matter almost unimpeded. Maybe they use gravitational waves. Maybe they encode messages in the cosmic microwave background, or in the orbits of planets, or in the structure of crystals. We wouldn't recognize any of these as communication because we're not looking for them. We're like someone trying to find a TV signal using a telegraph. The technology doesn't match. Or maybe they're not communicating at all. Maybe advanced civilizations go quiet deliberately. Maybe they realize that broadcasting your presence across the galaxy is dangerous. Maybe there are predatory civilizations out there, and the smart move is to stay hidden. This is sometimes called the dark forest hypothesis. The idea is that the galaxy is like a dark forest at night. There might be other hunters out there, but everyone stays silent and hidden because making noise reveals your position and makes you a target. Maybe every civilization that reaches a certain level of technology realizes this and goes dark. They listen, but they don't broadcast. They watch, but they don't reveal themselves. And so the galaxy remains silent, not because it's empty, but because everyone is hiding. Here's what we know. The universe is incomprehensibly vast. Distances between stars are measured in light years, and even the nearest stars are so far away that communication takes years and travel takes centuries or millennia. Time is a barrier as significant as space. Civilizations rise and fall on timescales that may not overlap. Even if intelligent life is common, the chances that two civilizations exist at the same time, close enough to communicate, and for long enough to have a meaningful exchange, are vanishingly small. The speed of light is an absolute limit, enforced by the structure of space-time itself. We can't cheat it. We can't go around it. We're stuck with it. And it means that the universe will always feel empty and isolated, even if it's teeming with life. Energy requirements for both communication and travel are enormous. Most civilizations probably can't or won't invest the resources needed for projects that might take thousands of years to produce results. And even if they do, there's no guarantee of success. The signals might not be detected. The probes might fail. The target civilization might be gone by the time you arrive. We might be surrounded by civilizations, but we'll never know. They might be out there right now, 1,000 light years away, looking at our sun through their telescopes, wondering if anyone lives here, sending signals we haven't detected yet or won't detect for another 1,000 years. And we're doing the same, looking at their stars, wondering, waiting, listening to silence. This is the universe we live in. A cosmos that, through its sheer scale and the fundamental laws of physics, keeps intelligent life isolated. Not through malice or design, but through indifference. The universe doesn't care if we're alone or not. It doesn't care if civilizations meet or remain forever ignorant of each other. It simply is what it is. Vast, ancient, governed by laws that make some things easy and other things almost impossible. So what do we do with this knowledge? Some people find it depressing. The idea that we might be alone, or that even if we're not, we might never meet another civilization, can feel isolating and sad. It touches on deep questions about meaning and purpose. If we're the only consciousness in an incomprehensibly vast universe, does that make us cosmically important or cosmically insignificant? If there are others out there, but we'll never meet them, never share our discoveries or learn from theirs, does that diminish the value of what we accomplish? Some philosophers and scientists have grappled with these questions. Carl Sagan, one of the most eloquent voices for space exploration, believed that the search itself gives meaning. Whether we find anyone or not, the act of reaching out, of trying to connect, reflects something fundamental about who we are as a species. We're curious. We ask questions. We build tools to explore. We create art and music and mathematics. We try to understand the universe and our place in it. That drive, that yearning to know, is part of what makes us human. And it matters whether or not anyone else is out there to appreciate it. But there's another way to look at it. If contact is nearly impossible, then every moment of existence is precious. Every discovery we make, every work of art we create, every kindness we show to each other, it all matters because it might be the only example in our corner of the universe. We might be the only minds capable of appreciating a sunset, of wondering about the stars, of asking why the universe exists. If we are alone, or functionally alone, because distance and time keep us separated from anyone else, then we carry the torch of consciousness in a vast darkness. We're the universe becoming aware of itself, matter organizing into patterns capable of looking back at the cosmos and understanding, even if only partially, how it works. That's extraordinary. That's worth preserving. Think about what consciousness represents. For billions of years after the Big Bang, the universe was just particles and energy, following physical laws, unaware of itself. Stars formed and died. Galaxies collided. Planets coalesced from dust. All of it happened mechanically, governed by gravity and electromagnetism and the other fundamental forces. No part of the universe knew it was happening. There was no perspective, no experience, no awareness. Then, at some point, on at least one planet, and possibly others, matter became complex enough to be aware. Neurons formed networks. Brains developed. Consciousness emerged. And suddenly, a tiny part of the universe could think, could wonder, could ask questions. We are that part. We're made of atoms, forged in the cores of ancient stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of it was created in stellar furnaces and scattered across space when those stars died. We're literally made of star stuff, to use Sagan's phrase. But we're not just star stuff. We're star stuff that has organized itself into a pattern capable of contemplating its own origins. We can look back across billions of years and understand where we came from. We can look out across billions of light years and map the structure of the universe. We can look forward and predict what will happen to the sun, the galaxy, the cosmos itself. That's unprecedented. As far as we know, nothing else in nature can do this. A rock doesn't know it's a rock. A star doesn't know it's a star. But we know we exist, and we know what we're made of, and we're beginning to understand how we came to be. That awareness, that capacity for understanding, it might be the rarest and most valuable thing in the universe. And if we destroy ourselves through war or environmental collapse or any of the other existential risks we face, we might be snuffing out the only candle burning in our corner of the cosmos. On the other hand, if we're not alone, if there are other civilizations out there facing the same barriers we are, then maybe our task is to last long enough that one day, somehow, we might find a way to reach each other. It won't be easy. It might take thousands or millions of years. It might require technologies we can't yet imagine. But it's not impossible, just improbable. And humans have a long history of doing improbable things. We've walked on the moon, an achievement that seemed like pure fantasy just a century before it happened. We've sent probes to the edge of the solar system and beyond, tiny machines carrying messages from Earth into the darkness. We've built telescopes that can see galaxies billions of light years away, looking back in time to when the universe was young. We've decoded the structure of DNA, understanding the molecular basis of life itself. We've split the atom, releasing energies that power cities and, unfortunately, also weapons. We've created computers that fit in our pockets and can access the sum of human knowledge. We've connected the world through communications networks that let us talk to anyone, anywhere, instantly. None of that was easy. All of it required overcoming barriers that seemed insurmountable. People said heavier-than-air flight was impossible. Then the Wright brothers proved them wrong in 1903. People said breaking the sound barrier would destroy aircraft. Then Chuck Yeager did it in 1947. People said reaching space was impossible. Then Yuri Gagarin orbited Earth in 1961. People said landing on the moon was impossible within a decade. Then Neil Armstrong stepped onto the lunar surface in 1969. We have a tendency to underestimate what's possible, to assume that current limitations are permanent. But history shows that determined effort, clever engineering, and scientific understanding can overcome obstacles that seem absolute. Maybe interstellar contact is the same. Maybe it's the next great challenge, the thing that will take not years or decades, but millennia to achieve. Maybe our descendants, if we have any, will be the ones to finally bridge the gap, to send a message that's received, to make contact with another mind from another world. Maybe they'll develop technologies we can't imagine, ways to communicate faster than light or travel between stars in reasonable time frames. Maybe they'll discover new physics that changes what's possible. Or maybe they won't. Maybe the barriers are too high. Maybe the universe really does make it impossible. But the attempt matters. The effort matters. The fact that we're here, thinking about this, wondering, searching, that matters. Even if we never make contact, the search itself transforms us. It forces us to think beyond our immediate concerns, beyond our planet, beyond our species' brief existence. It connects us to something larger, the cosmic story, the grand narrative of matter and energy evolving over billions of years. We're part of that story. Maybe a small part, maybe a crucial part, we don't know yet. But we're here, we're aware, and we're trying to understand. That counts for something. Consider what we've accomplished in just the last few decades with our search for extraterrestrial intelligence. We've built radio telescopes like the Arecibo Observatory and the Very Large Array, scanning the skies for signals. We've developed protocols for what to do if we detect something, who to notify, how to verify it's real, whether to respond. We've sent our own messages into space. like the Arecibo message in 1974, a brief radio transmission aimed at a globular cluster 25,000 light-years away. It'll arrive in about 25,000 years. If anyone's there and they respond immediately, we'd receive their reply in about 50,000 years. None of us will be here to see it. But we sent it anyway because the gesture matters. We've attached plaques and records to our deep space probes. Pioneer 10 and 11 carry plaques with information about Earth and humanity. Voyager 1 and 2 carry golden records with sounds and images from our world. These objects are traveling beyond the solar system, into interstellar space, where they'll drift for millions or billions of years. The chances of anyone finding them are essentially zero. Space is too big, and the probes are too small. But if someone does find them, someday, somehow, they'll know we existed. They'll know we tried to reach out. We've also been listening. The SETI Institute and other organizations have been scanning radio frequencies for decades, looking for patterns that might indicate intelligent origin. They've developed sophisticated algorithms to filter out natural noise and identify potential signals. They've enlisted volunteers around the world through projects like SETI at Home, distributing the computational work of analyzing data. So far, we've found nothing conclusive. There have been a few intriguing signals over the years. The WOW signal, detected in 1977, was a strong narrowband radio signal that lasted 72 seconds and has never been detected again. It had many characteristics expected of an extraterrestrial signal, but it was never confirmed, and its origin remains unknown. More recently, we've detected fast radio bursts, brief pulses of radio emission from distant galaxies. For a while, some speculated they might be artificial, but we now think they're natural astrophysical phenomena, possibly from magnetars or colliding neutron stars. The search continues. New telescopes are being built. New techniques are being developed. We're expanding the search beyond radio waves to include optical signals, laser pulses, and even looking for signs of advanced technology like megastructures or atmospheric pollution that might indicate industrial civilization. We're learning more about exoplanets every year, identifying which ones might be habitable, which might have atmospheres, which might show signs of life. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheres of distant planets, looking for chemical signatures that might indicate biological activity. If we find oxygen and methane in the same atmosphere, that could suggest life, because these gases react with each other and wouldn't persist without something constantly replenishing them. On Earth, that something is life. Photosynthesis produces oxygen. Bacteria and other organisms produce methane. Finding both together on an exoplanet would be strong evidence, though not proof, of biological activity. We're getting closer to answering one of humanity's oldest questions. Are we alone? We might get an answer in our lifetimes, or our children's lifetimes. It might be, yes, we found evidence of life on another world. Or it might be, we've looked and found nothing. Either answer would be profound. If we find life, even simple microbial life, it would mean the universe is full of biology. Life wouldn't be a fluke that happened once, but a natural consequence of chemistry and physics, likely to occur wherever conditions allow. That would be extraordinary. If we don't find life, if we search thoroughly and find nothing, that would be equally extraordinary. It would mean we're rare, possibly unique, possibly alone in a vast empty cosmos. That would change how we see ourselves and our responsibility to preserve life and consciousness. But finding evidence of simple life and making contact with intelligent life are different challenges. Simple life might be common. Intelligent, technological life might be rare. And even if it's not rare, contact might still be impossible for all the reasons we've discussed tonight. We've launched probes into space, carrying messages for any civilization that might find them. Voyager 1 and Voyager 2 both carry golden records, phonograph records, encoded with sounds and images from Earth. They include greetings in 55 languages, music from different cultures, pictures of humans and animals, and landscapes, scientific information about our location and our biology. These probes are traveling out of the solar system into interstellar space. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. If there's anyone there, if they detect the probe, if they retrieve it, if they can figure out how to play the record, they'll receive a message from us. A message from Earth in the year 1977, delivered tens of thousands of years later to beings we can't imagine. It's unlikely anyone will ever find it. Space is so vast and the probe is so small that the odds of detection are infinitesimally small. But we sent it anyway. Because the alternative is to do nothing, to accept isolation without attempting to reach out. And that's not who we are. We're a curious species. We ask questions. We explore. We reach for things beyond our grasp, knowing we might fail, but unable to resist trying. That impulse, that drive to connect, to understand, to reach beyond ourselves, it's one of the most fundamentally human things we do. And even if the universe makes it impossible for civilizations to meet, even if we're shouting into an infinite void that will never answer, we'll keep trying. Because the act of reaching out, the hope that someone might be listening, that's what makes us human. So tonight, when you look up at the stars, think about what's out there. Maybe it's nothing. Maybe we're alone, the only consciousness in a galaxy of lifeless rocks and gas. Or maybe it's teeming with life, with civilizations rising and falling, broadcasting and listening, hoping and waiting, just like us. Maybe they're out there right now, looking at our sun, wondering if anyone is here. Maybe they're sending signals we haven't detected yet. Maybe in 1,000 years, our descendants will pick up a message, decode it, and realize that we were never alone. Or maybe the silence will continue forever, the distance and time and physics of the universe, ensuring that we remain isolated islands of consciousness in an ocean of emptiness. We don't know. We can't know. Not yet. All we can do is keep looking, keep listening, keep hoping, and try to build a civilization that lasts long enough that if contact is possible, we're still here to experience it. That's the challenge. That's the task we've inherited. To survive long enough, to grow wise enough, to reach far enough, that maybe, just maybe, we can overcome the barriers the universe has placed between us and anyone else out there. It won't be easy. It might not even be possible. But it's worth trying. Because the alternative is to accept that we're alone, that we'll always be alone, that the universe is a lonely place where intelligence arises and dies in isolation, never knowing if it's the only one. And that's a future we don't have to accept. Not yet. Not while we still have the will to reach out, to search, to hope. So we keep searching. We build bigger telescopes. We listen to more frequencies. We scan more stars. We send more probes. We keep trying, year after year, decade after decade, knowing that the odds are against us, but unable to give up. Because somewhere out there, maybe someone else is doing the same thing. Maybe they're listening too. Maybe they're hoping too. Maybe one day, across the incomprehensible distances of space, across the vast gulfs of time, two signals will cross in the darkness. Two civilizations will make contact, and the universe will become a little less lonely. That's the dream. That's what keeps us searching. Not certainty, but possibility. Not knowing, but hoping. The universe might make it impossible for civilizations to meet, but it doesn't make it impossible to try. And as long as we're here, as long as we're capable of looking up at the stars and wondering, we'll keep trying. Because that's what we do. That's who we are. We're the species that reaches for the impossible, that dreams of touching the stars, that refuses to accept isolation as the final answer. We're humanity, and we're still here, still searching, still hoping, still reaching out into the darkness, waiting for an answer that may never come, but reaching anyway. Because even if the universe makes it impossible, even if we never make contact, even if we remain alone forever, the act of trying matters. The search itself has meaning. And as long as we exist, we'll keep searching. We'll keep listening. We'll keep hoping that one day, somehow, we'll find that we're not alone after all. Thanks for staying with me through this long journey across space, time, and the barriers that keep us isolated. The universe is vast, beyond comprehension, and the odds are stacked against us. But we're still here, still looking up, still wondering, and that, in itself, is extraordinary.